Hello mathematicians, thanks for joining me today as we continue our lecture on mappings. So, where we left off is we had been talking about mappings. We talked about what it meant to be one-to-one and what it meant to be onto. And so these are going to be relations from a set S to a set T. And so we want to determine how many such mappings are there from S to T. How many are there that are onto? How many are there that are one-to-one? So in order to determine that, we're actually going to find each of these by drawing a diagram to determine what all the mappings would look like and which ones are onto and which ones are one-to-one. So as we try to find all the mappings from S to T, what we're going to do is just look at, well, here's X, Y, Z, and I'm going to map to 1, 2, 3, so I want to think about all the possibilities. Well, what we can get is for mappings, here X can go to 1, or it can go to 2, or I can go to 3. So I have 3 different options for where X can go. Now, if I look at then Y can go to 1, it can go to 2, and it can go to 3. So I have 3 different options for Y, and the same thing with Z. I have 1, 2, 3 different options, and so the idea is that I could have something like X goes to 1, Y goes to 2, and Z goes to 3 would be one mapping. Now, what happens here is if I want to determine all possible mappings, I would think, well, what are all of my options? So now I would start with X and I would have 3 options. And then Y would give me, based on X's option, it would give me 3 more options. So notice what I'm doing is I'm choosing something for X and then choosing the image for Y. So far I have 3 options and 3 options, so I use the multiplication principle from counting to say, well, I have 3 times 3 options. Again, for Z, I would have 3 options. So I get 3 times 3 times 3 options, where X can go at any one of these 3, Y can go to any one of those 3, and Z can go to any one of those 3. And I end up with a mapping from S to T. So I will get 3 cubed, or 81 mappings from S to T. On the other hand, if I want to count onto mappings, what I have to do is I have to make sure that 1, 2, and 3 get mapped to from somewhere. So what I'm going to do is think about, well, if 1 has to get mapped to from somewhere, what are my options? Well, either X can go to 1, Y can go to 1, or Z can go to 1. So what we had so far is picking which goes to 1, I have 3 options. Then I would move on to 2 and say, well, I need it to be an onto mapping. So what has to happen here is I have, well, you would think I'd have 1, 2, 3 options, but if I pick Z here, notice that that's not a mapping. So I really only have 2 options, is either X goes to 2 or Y goes to 2. So let's say X goes to 2. So far what I have is I picked what goes to 1, I had 3 options. Since I've already defined what went to 1, I can't pick that for what goes to 2, so I'll have 2 options for what goes to 2. Now once I get to 3, what I have is, well, I only have 1 option left. Y would have to go to 3 because the other ones have already been used. So if I want to find the total number of onto mappings, I would get 3 times 2 times 1, which is also 3 factorial, or 6 onto mappings. Notice there is a big difference here between the 81 total mappings and the 6 onto mappings. So being onto is a much more restrictive thing than just being a mapping. If I now want to find one-to-one mappings, what I want to do is make sure that each of these X, Y's, and Z's goes to different spots. So here the pointers goes, I would start with X. I would say X can go wherever it likes. So X has 3 options. So let's say it goes to 3. Now I would move on to Y and say how many options are there for Y goes? Well, Y can't go to 3 because we want it to be 1-to-1. So therefore Y either has to go to 1 or 2. So I'm going to have 2 options for Y. And so let's say it goes to 2. Now when I get down to Z, notice that X has already gone to 3, Y has gone to 2, so there's only 1 option left for Z. So when I'm finding one-to-one mappings, notice that I would indeed have 3 times 2 times 1, or 3 factorial, which is also 6. And so in comparing here, we got the same number of onto as one-to-one mappings. That won't always be the case, but there's something going on with this example that is making that happen. And the distinction, remember, was when we're finding onto, we said, okay, we had to map to here how many options, and I worked through my range, whereas for one-to-one, I worked with my domain. Now for another example, we're going to look at a family of mappings. So it's let A and B and Z cross Z, be an ordered pair of integers. So what I want to do is I want to define alpha as alpha sub AB is a mapping from Z to Z, where alpha sub AB of n is AN plus B. So now this is a family because I get a different function for each A and each B. So for example, if A was 1 and B was 2, I would get 1n plus 2. What I want to show is that, or what I want to determine is that for which pairs of A and B is that mapping going to be onto, and which pairs of A and B is it going to be one-to-one. So we'll work through and figure out which of those are one-to-one and which of those are onto. So now what we want to determine is that for this alpha sub AB, which A's and B's give us an onto mapping. So in order to do that, I'm just going to think about, well, if I had some Y and Z, for which A's and B's would I get out that I could always get Y for some X? So that would mean that, well, what I want to do is assume that I had alpha of AB of X is equal to Y, and I want to find what X would be, and I want to determine, okay, for what integers can I always find such an X? So what I would then have is AX plus B is equal to Y. And so I would get AX is equal to Y minus B, and X is equal to Y minus B over A. Now, when would this be possible to always solve for X? Well, notice that it's possible to solve for X if Y minus B is divisible by A. However, because I can pick any Y I want, this has to be true for all Y to make this an onto function. So what I can do in particular is pick this Y so that it's Y plus B, or 1 plus B, because 1 plus B minus B is 1. And so what I could end up with is that I'd have to have a solution to, say, 1 over A. So I'd have to have an X is 1 over A, for example. However, notice that if I pick an integer other than 1 or negative 1, 1 divided by A is not going to be defined in the set of integers. So if we pick 0, it's not defined. 1 over 2 is not defined as an integer because 1/2 is not an integer. Same thing with 1 over negative 5 is not an integer. So what we notice is that we're going to be able to solve this equation if and only if A is a number which divides 1. Well, the only divisors of 1 are 1 and negative 1. So what we're going to say is that this is onto if and only if A is equal to either 1 or negative 1. So now we can actually go ahead and prove that it's onto if and only if A is 1 or negative 1. But notice that it didn't matter what B was as far as onto. Alright, so I started my proof of this direction, and we were going to say that if it is onto, then A has to be equal to 1 or negative 1. So instead of doing a direct proof, we're going to do a proof by contrapositive, and we're going to assume that A is not 1 or negative 1. And what we want to show is that alpha of AB is not onto. So if we want to show this is not onto, we have to say there exists a Y in Z where we cannot get alpha where there is no X with alpha sub AB of X equal to Y. So if we want to show it's not onto, we have to find a Y which does not get mapped to for any X in Z. And all we get to assume here is that A is not 1 or negative 1. So now notice that as we were doing this, when we were writing up, okay, well, is it onto or not, we went through and we solved for if we have y, this is what x should be. And we decided that, well, if we try to take 1 divided by a, we're not going to get out an answer unless we have 1 or negative 1. And so the y that corresponds to that is let y equal 1 plus b. Note that y is in z. Since b is an integer, if I take 1 plus b, I get an integer. Therefore, y is an integer, and this is the one we show that we can't map to. So, what we're going to do now is actually, well, to show that we can't map to it is actually difficult. So, by way of contradiction, assume that we can. So I'm going to assume there exists an x such that alpha sub ab of x is equal to y. Well, what does that mean? Well, that means ax plus b is equal to y. Sorry, y, 1 plus b was my y, so that's when I want to plug in for y. So I get ax plus b is equal to 1 plus b. Now I'm going to need some more room here. So what that means is that if I subtract b from both sides, ax is equal to 1. So therefore, x is equal to 1 over a. Now we assume that this was an integer solution, but we're saying that x is 1 divided by a. Since a is not 1 or negative 1 and a is an integer, that a does not divide 1. So 1 over a is not an integer. So what we get is that, well, x is an integer and x is not an integer. Therefore, that's a contradiction. So what does that mean? Well, that means for y equals 1 plus b, we cannot find an x that maps to that y value. Hence, if a is not 1 or negative 1, our mapping is not onto. So by the contrapositive, if our mapping is onto, a has to be 1 or negative 1. All right, so now what we're going to look at is this 1-to-1 for a and b? And so we just want to think about, well, if it's 1-to-1, that means that if I take alpha sub ab of x1 and let that be alpha to sub ab of x2, if it is going to be 1-to-1, I'm going to be able to show that x1 is x2. If it's not 1-to-1, I'm going to find an example where this can be true, but x1 is not equal to x2. So what I'm going to do is just say, okay, if these are equal, what does that mean? Well, what that means is that a x1 plus b is equal to a x2 plus b. Now I can subtract b from both sides, and I get a x1 is a x2. Now here's the tricky part, is that I can divide by a and I get x1 is equal to x2, except I can't divide by all integers. So if this was 2, 2 divided by 2, that works. However, I can't divide by 0. So what I would say is that if a is not 0, then I can divide by a and I get that x1 is equal to x2. Hence, what I have is that if a is not equal to 0, I've actually proven that this is 1-to-1. So what I can say is, I don't even really have to rewrite anything, is I'll just let x1 and x2 be in the set of integers with alpha of x1 equal to alpha of x2. Then I get that this is true, and if a is not 0, then this is true. So if a is not 0, it's a 1-to-1 mapping. All right. To show that that's an if and only if is, on the other hand, I can let a equal 0. Then let's let x1 equal anything, so 1, and x2 equal 2. In that case, what we want to show is that alpha of x1 is equal to alpha of x2. That would imply that this is not 1-to-1. So if a is equal to 0, then alpha sub ab of 1 is equal to a times 1 plus b is equal to 0 times 1 plus b is just b, but that's also equal to 0 times 2 plus b, which is alpha sub ab of 2. So that is, if I plug anything in, if a is 0, I'm just going to get out b every time. So therefore, since I'm getting out b every time, alpha of 1 is equal to alpha of 2. Since 1 is not equal to 2, we get that this indeed is not one-to-one mapping. So what we have is that alpha sub AB is 1 to 1 if and only if A is non-zero. Next, we want to show the other direction, and that is if A is equal to 1 or negative 1, then alpha sub AB is indeed onto. So what we're going to have to do here is we're going to say let y be in the codomain, the set of integers. We have to show that there exists an x that gets mapped there. So what was our x going to be is, note that if we go back to the work we did before, if we let x equal y minus b over a, then we're going to get that it's going to map to where I want. Now the point here is that, well, y minus b. Y is an integer minus b is still an integer. Any integer is divisible by 1 or negative 1, so this is indeed an integer. So what I have is x is an integer, and furthermore, alpha sub ab of x is equal to a times x plus b, which is a times y minus b over a plus b, which is, the a's cancel, so I get y minus b plus b, which is y. Hence, we have some integer that gets mapped to y for any integer y. So therefore, this mapping will be onto. So we have that for this family of mappings. It is going to be onto if and only if A is 1 or negative 1. Now another thing we can do with mappings is that we can compose them. So that is, if I want to find the composition of mappings or the composition of functions, what I have to have is a mapping from S to T and another mapping from T to U. So then we define beta of alpha as S to U, where x is mapped to beta of alpha of x. So we can look at this graphically, and we'll see what that looks like. All right, I wanted to look at pictorially what a composition will look like. So the idea is that I start with a set S, and I go to a set T, and then I have a set U. And so what I have is, okay, alpha is going to tell me how to get from S to T. So here's alpha. Beta is then going to tell me how to get from T to U. So beta will look something like that. Now, if I want to find beta of alpha, well, what that means is that if I want to take an arbitrary element, let's say x, where x is in S, here's x. So I'm going to take x and I'm going to map it over to T by whatever alpha tells me to do. So I'm plugging into alpha first. So if I'm reading this with compositions, you actually end up reading right to left because it means plug x into alpha and then the answer into beta. So here is x, here is alpha of x. But now what I'm going to do is I'm going to take this, whatever that happens to be under beta, and I'm going to get beta of alpha of x. So in the end, this turns into one mapping, which goes directly from x over to beta of alpha of x. So the idea is that instead of going from here to here and then here to here, the composition is just going to go directly from here to here. So we end up in the same spot, either taking 2 steps or 1, but finding the composition mapping means that we're just doing this all in one step. So in the end, we're mapping things in S into things in U. For our next example, let's look at S and T and U are defined as here, and we have alpha is given by x goes to 2, y goes to 1, and z goes to 3, and we've also defined beta in a similar manner. What we're going to want to do is we want to figure out what beta of alpha looks like and what alpha of beta looks like. So we'll go ahead and draw these out and see what happens. All right, so now we're going to look at a composition of mappings, and we're going to do this graphically as well. And so what I'm going to have here is the set S is equal to x, y, z. The set T is equal to 1, 2, 3. And the set U is equal to A, B, C. So if I look at what this mapping tells me to do, it tells me to send x to 2, y to 1, and z to 3. So this will be my mapping alpha. I then have beta defined as, well, 1 goes to B, 2 goes to C, and 3 goes to A. So what I want to do is find beta of alpha. And so I'm going to say that, well, in the end, what I'm going to do is I'm going to start in S, and I'm going to map into U. So I'm going to take a number or a letter here and plug it into alpha, and then plug the answer into beta. And so what I'm going to get is I'm going to get beta of alpha is defined as a mapping from S to U, given by x is going to map to, well, let's determine where x goes. X went to 2, and then 2 went to C, so I started at x and ending at C. If I look at y, I went from y to 1 to B, so y is going to map to B. And if I look at z, z is going to map to 3 to A, so z maps to A. So what I get is that beta of alpha is the mapping which sends elements from S to elements of U, which sends x to C, y to B, and z to A. Now, if I had tried to find alpha of beta, what would that mean? Is that means actually go beta first. So let's find alpha of beta. I'm going to try to map then T would go to U, and then I'd have to end up at S. So what is alpha of beta of 1? Well, this is alpha of beta of 1 is B. But now, what that means is, what is alpha of B? Well, if I look at alpha, is B in the domain? No, it is not. So this does not exist. So because I did alpha or beta of 1, and then I try to take alpha of B, I got does not exist. The point I'm trying to make here is that even though beta of alpha is well defined, alpha of beta won't be. Therefore, what I'm trying to point out is that the order of the composition does matter. So that is, if I switch the order of alpha and beta, I get out something different. So we really do have to be careful about the ordering. And this is saying, okay, well, I need to do beta first, then alpha. So that's not defined. So make sure that I write beta of alpha. So I do alpha first, then beta. Because again, switching the ordering can make a huge difference. So you really want to be careful about that. So for another example now, we'll have alpha as a mapping from R to R, and beta as a mapping from R to R. And so here again, we'll find alpha of beta and beta of alpha. So now we're going to find another composition, alpha of beta and beta of alpha, where we're dealing with mappings that are not defined just by what goes to what, but rather defined by a function notation. And so what we're going to have is, I want to find alpha of beta of x. And so if I want to find alpha of beta of x for this example, what I have was, well, beta of x is just equal to x minus 1. So what I get is alpha of, I plug x into beta, I get x minus 1. Now alpha of x is equal to x squared. So we're going to plug in, instead of x, we're going to plug in this whole thing into alpha. And so I'm going to get x squared. But on the inside is x minus 1. So I end up with x minus 1 squared. So alpha of beta of x is x minus 1 squared. On the other hand, beta of alpha of x is equal to,
Well, I'm going to plug x into alpha, so I'm going to get x squared. And then into beta, I'm going to plug this. So remember, beta was x minus 1. So instead of x minus 1, I'm going to get x squared minus 1. So alpha of beta was x minus 1 squared, but beta of alpha was x squared minus 1. Note again, these two are not equal, so we don't get the same answer both ways. So again, we do have to be careful about the direction that we're doing the composition in.
All right, so now we're going to work it in general. We're going to say alpha is a mapping from S to T and beta is a mapping from T to U. So then based on whether or not alpha, beta are 1 to 1 or onto, can we determine something about the composition? Or if we know something about the composition, can we determine something about the individual mappings? And so we have 4 theorems here that we'll actually go through and prove.
Now we're going to try to prove some things here. And so I'm actually going to do these pictorially. You could follow through and do these precisely, but I want to just give an idea of what's happening. So we have S, T, and U. We have alpha. We have beta. And the first thing is that if alpha and beta are onto, I want to show that alpha composed, or beta composed with alpha is onto. So what does that mean? Well, what that means is that I want to show that for everything in U, I have to find something in S such that this will get mapped to here under beta of alpha. And I get to assume that alpha is onto and beta is onto, and I have to show that's possible. All right. Well, how am I going to do that? So the point is I'm letting y be arbitrary, but what I know is that beta is onto, so that means that there is some, say, z, such that z is mapped to y under beta. Again, that's true because beta is onto, therefore for every y in U there exists a z such that beta of z is equal to y. But now z is in T, therefore there exists some x in S such that x is mapped to z under alpha. Again, there's something in here, therefore this is onto, so there had to be something in here that mapped to here. So what I did was I said, okay, if I wanted to find where I should have started, I started at y, I found the z, and then from the z I could find the x. But now if I find beta of alpha of x, well, beta of alpha of x is equal to, well, alpha of x is equal to z, and beta of z is equal to y. So beta of alpha of x is equal to y, and that will work for any y in our U. Hence, beta of alpha is going to be onto from S to U. All right, so now we're working on number 2, and we get to assume that beta of alpha is onto, and I want to show that beta is onto. So what we get to assume is that there exists an x such that beta of alpha maps x to y. So there exists an x such that beta of alpha of x is equal to y, because that's what it means for beta of alpha to be onto. What do I have to show is that for every y, there exists a z in T such that beta of z is equal to y. Well, notice there isn't actually a lot of work to do here because alpha of x has to be equal to something. So alpha of x is in T, and beta of alpha of x is equal to y. Hence, for every y in U, there exists a z in T, namely alpha of x, which gets mapped to y. So if alpha or beta of alpha is onto, beta had to be onto, because there had to be something in T which then got mapped to that y. All right, for our next thing we're going to look at, well, if alpha is 1 to 1 and beta is 1 to 1, I have to show that beta of alpha is 1 to 1. So what that means is that if I take beta of alpha of x1, and I assume that's equal to beta of alpha of x2, I have to be able to show that x1 is equal to x2. Well, what's happening here is that beta of alpha of x1 is equal to beta of alpha of x2 is equal to y? Well, what has to happen here is that, well, since this is 1 to 1, I can't have this picture, right? Because that would be not 1 to 1. So since y is in u, there's only one thing in t which could map to it. Well, what does that mean? Is notice that alpha of x1 and alpha of x2 are in t, but beta of this is equal to beta of this. So that implies alpha of x1 is equal to alpha of x2. So beta of this thing in t is equal to beta of this thing in t. So these two things must be equal because beta is a 1-to-1 mapping. Now notice by the same argument, if I have this element here, I can only have one thing in S that gets mapped to that thing there because alpha is 1 to 1. So therefore, well, notice that x1 gets mapped to here and x2 gets mapped to here. So those two things have to be the same thing because I can only have one thing going here. So because alpha is 1 to 1, that implies x1 is equal to x2. So what do we get in the end? Is, well, because beta is 1 to 1, alpha of x1 is equal to alpha of x2, and because alpha is 1 to 1, x1 is equal to x2. Therefore, if beta of alpha of x1 is beta of alpha of x2, x1 is equal to x2, so beta of alpha has to be 1 to 1. Alright, so the last one we want to show is that if beta of alpha is 1 to 1, then alpha has to be 1 to 1. I'm actually going to prove this one through the contrapositive, and I'm going to assume that alpha is not 1 to 1, and I'm going to show that beta of alpha can't be 1 to 1. So what does that mean? Well, if alpha is not 1 to 1, then I have an x1 and an x2 in S, which gets mapped to the same point. Let's call this Z. Now, that's the definition of not being 1 to 1, is that there exist at least two elements that get mapped to the same element in T. Well, since I have two things get mapped to the same thing, notice that Z is in T, so under beta it has to go somewhere, Y. So if I follow this, what I get is that beta of alpha of x1 is equal to, well, alpha of x1 is Z, beta of Z is Y, so this is Y. Also, beta of alpha of x2 is equal to, well, alpha of x2 is Z, beta of Z is Y. So if alpha was not 1 to 1, then we would have beta of alpha cannot be 1 to 1. Hence, by the contrapositive, if beta of alpha is 1 to 1, that implies that alpha has to be 1 to 1. So if we have a mapping alpha from S to T, if we can find a mapping beta from T to S such that beta of alpha is equal to the identity mapping on S, and alpha of beta is the identity mapping in T, we're going to say that beta is the inverse of alpha, and therefore alpha is an invertible mapping. Alright, so what I have here is we're talking about inverse mappings. So if I have S to T, and I'm going to have alpha maps from S to T, the idea is that for any x in S, I'm going to map to some y in T. So here's x, here's y, here's what alpha does. Now the point is that I want to define my inverse, which I'm calling beta here. Beta is going to go back from T to S, and what I want is that beta of alpha of x is going to be equal to x because I want this to be the identity mapping. Therefore, if beta of alpha of x is equal to x, well, alpha of x is equal to y, so beta of y has to be equal to x. So what beta ends up doing is undoing what alpha did. So if alpha mapped x to y, beta is going to map y to x. And if that's true for all the elements in x and all the elements in T, then beta of alpha of x will always be equal to x. But by the same token, notice that if we take beta maps y to x, alpha is mapping x to y, then if we find beta of alpha of beta of y, we're just going to get out y for all the y in T. So in either case, we're just going to end up exactly where we started at. So the composition of these two becomes the identity mapping. Now, one of the identity mappings is on S, because it's sending things in S to things in S. The other one's on T, because it's sending things in T to in T. But the composition in both directions is just an identity mapping. And so that's what we're going to call an inverse.
So now we have two functions here, x maps to x minus 1 and x maps to x squared. And what I want to determine is which of these are invertible. And so we'll prove that one of them is invertible and one of them is not.
All right, so what we have here are two mappings, and we want to determine which one's invertible. And so the first one, we're going to map from R to R given by x goes to x minus 1. So if we do that, what I'm going to do is first off just graph it. And so if I graph x minus 1, it looks like this. Now in order to be invertible, the idea is that I want to pick x, I'm going to go up to y, and so that's going to be alpha of x is going to send x to this y. To find an inverse, what I have to be able to do is go from this y back to this x. So what types of things could happen that would make this mess up is that, well, notice that when I go from y's to x's, again, I have to have a mapping. So if I had something like this, my y would actually go to two spots. So that beta would not be an inverse because it has one thing going to two things, which would make my beta a non-well-defined mapping. On the other hand, if I had some y that didn't get mapped to, well then I can't go backwards from that y. So if I can't go backwards from that y, I'm not going to have an inverse. Therefore, if I go back to x minus 1, I say, well, it looks like for every y, there's going to be exactly one x associated with it. Therefore, I think this will be invertible. All right, so now how do I prove that? Well, now I actually go through and do some calculations, and the point is that I want, okay, if x minus 1 is equal to y, can I find y that, or can I find a function that will map y back to x? So what I'm going to do is solve for y in terms of x, and I get x is y plus 1. Therefore, if alpha of x is equal to x minus 1, we're going to define alpha inverse of y to be y plus 1. So, the first thing I want to point out is that this is a well-defined mapping on the real numbers because I take a real number, I subtract 1, I get a real number. This is a well-defined mapping on the real numbers because if I add 1, I get a real number. So, let's do our proof. Our theorem is if alpha of x equals x minus 1, then alpha is invertible. Proof. Note that alpha inverse from R to R given by alpha inverse of y is equal to y plus 1 is a well-defined mapping. That is, for each input, I get out exactly one output. I start with a real number, I end with a real number. Then, what I get is that alpha of alpha inverse of y is equal to alpha of y plus 1 is equal to y plus 1 minus 1 is equal to y. And then I do the same thing in the other direction. Alpha inverse of alpha of x is equal to alpha inverse of x minus 1 is equal to x minus 1 plus 1 is just x. So notice we had to do the composition in both directions because the composition could change in direction. But in both cases, we started here at y and ended at y. Here I started at x and ended at x. So in both cases, I got the identity mapping. Therefore, this is the inverse of this. Therefore, this mapping is invertible. So to prove that something's invertible, we have to find the inverse, and then we have to show that it satisfies the properties of being an inverse. All right, so now if I look at x squared, what x squared looks like is this. So what I want to think about is that I want to send my x's to my y's, and so my inverse should send my y's back to unique x. But if I pick this y, notice that it goes to 2x's. And if I pick this y, it goes to 0x's. So just by looking at this, we notice that the inverse mapping will not be well defined because a y will go to, there's places where it's going to 0, there's places where it's going to 2. So in general, we don't always have the case that y always goes to exactly one spot. So we would say x squared is not invertible. All right. So how would we prove that x maps to x squared is not invertible? So what we have to show is that, well, if it was invertible, we'd have a mapping from R to R which undoes this. So what we'd have to have is that, assume that this, let's call this one alpha here. Assume alpha is invertible. Then alpha inverse from R to R given by alpha inverse of y is equal to x if x squared is equal to y is well defined, or is a mapping. So if I ever have alpha inverse of x of y is equal to x, so for any y, I get out an x, whenever x squared is equal to y, then there has to be, well, for each y, there has to be only one answer. Well, there has to be one and only one answer. However, let's just pick one where that doesn't happen. We could pick 4, and we could find 2 answers. So if y is 4, then x can be plus or minus 2. So for y equals 4, we get out 2 answers. Or you could say negative 1. If y is negative 1, then I need an x squared equal to negative 1. I'm going to get out no answers. So I'm just going to say here, if y is equal to negative 1, then we have x squared is equal to negative 1 for some x in R. This is a contradiction because the square root of negative 1 is not a real number. So therefore, by assuming that it was invertible, we got, okay, well, if y was negative 1, I can't find an x in the real numbers. Therefore, this cannot be an invertible mapping.
Now, hopefully we gained some insight from the last one, but what we're going to notice is that a mapping will be invertible if and only if it is both one-to-one and onto. So what we'd want to do is actually prove that if we're one-to-one and onto, we're invertible, and if we're invertible, we're one-to-one and onto.
All right, kind of recapping what we saw in the last one, the idea was we want to show that alpha is invertible if and only if it is one-to-one and onto. So if alpha is a mapping from S to T, the idea is that if it's not one-to-one, so if I'm not one-to-one, when I try to find the inverse mapping, I'm going to have one thing in the domain that gets mapped to 2 things in the range. Therefore, the inverse is not a mapping because a mapping has everything in the domain goes to one thing in the range. All right. If we're not onto, then there exists something in here which does not get mapped to over here. So when I try to do the inverse, alpha inverse of y is going to be undefined. Therefore, the inverse will not exist as a well-defined mapping. So if I'm not one-to-one, I'm not invertible. If I'm not onto, I'm not invertible. So now let's suppose that I am one-to-one and onto. Well, that means that for every x, this goes to y, and there's only one x that goes to this y, and for every y, there's something that goes there. So if I think about an arbitrary thing over here, just because I've already used y, I'm going to use w now. Well, I know that something goes here, and only one thing goes there, so if I go backwards, well, when I'm going backwards, I can't go back to 2 spots because that would imply I'm not one-to-one. And I have to go back somewhere because I'm onto. So therefore, if I'm invertible, if and only if I'm one-to-one and onto.
Well, thanks for watching our lecture on mappings. I hope that that was helpful and that you learned something along the way. I will provide some links in the description for other helpful posts to help you along with the way.